the forest is not silent. Even in its stillness, every tree, insect and shadow trembles with signals, some too subtle for the human ear, some vibrating through the soil, some etched in the nervous systems of animals that live in constant anticipation of death. In this hidden network, one figure moves like a living surge of voltage, the jaguar. The camera closes in on the shifting light of the understory, where leaves stir without wind and river mud carries faint impressions of pores. From the shadows, the animal emerges. Muscles ripple under patterned skin like tightly coiled wires ready to discharge. A low growl escapes its chest, not just a sound, but a frequency that rattles the canopy, sending monkeys scrambling into higher branches and birds launching into the air. In that single moment, the forest responds as if struck by an unseen current. The jaguar, Panthera onca, is the apex predator of the Amazon basin, its power unmatched not by size alone, but by design. Smaller than lions or tigers, it is nonetheless more compact, built with astonishing density. A typical adult may weigh between 80 and 120 kilograms, but nearly every gram is muscle, tendon, and bone engineered for explosive force. Unlike the long, lean frames of cheetahs or the endurance-driven bodies of wolves, the jaguar is built to unleash sudden, devastating energy. Its forelimbs are thick, its chest broad, its bite force the most powerful of any big cat, capable of crushing through bone and turtle shell alike. Where lions suffocate their prey and leopards pierce soft throats, the jaguar kills with a precision that is almost surgical, a single bite through the skull, puncturing directly into the brain. Evolution has armed it with a predator's equivalent of a circuit breaker, one decisive switch that turns life to stillness in an instant. Yet the jaguar's true power does not lie in its hunting alone, but in the ripples its presence sends throughout the ecosystem. In ecology, scientists call this the ecology of fear, a force by which predators alter not just the population numbers of their prey, but their very behavior. Capybaras grazing at the water's edge shift into tighter herds, nervous and vigilant, when jaguars prowl nearby. Deer alter their grazing routes, even changing the times of day they move. Even fish are influenced, as jaguars occasionally dive into rivers to snatch them, a spectacle rarely seen but often remembered. The mere possibility of an attack forces countless animals to adapt in advance. Fear becomes a pressure as real as hunger or climate, shaping the daily patterns of life. Imagine the forest floor as a vast electrical grid. The jaguar is not just a predator, but a surge of current that arcs across this web. Every step it takes vibrates into the soil, carrying olfactory traces of musk and urine that serve as warnings to those able to interpret them. Jaguars mark territories that may span up to 50 square kilometers, vast stretches of jungle that overlap only slightly with rivals. Within these boundaries, their presence is felt even in absence. Prey animals read the scent marks, the broken branches, the faintest trace of movement in the undergrowth, and respond accordingly. Like electrons in a circuit, they alter their flows, divert their paths, redistribute their activity to minimize risk. What results is not chaos, but a restructured order of energy with the jaguar at its core. The adaptations that allow this predator to dominate are as fascinating as the fear it creates. Its spotted coat, patterned with rosettes that dissolve into the forest's dappled light, is a camouflage born from millions of years of coevolution with this environment. Each patch of fur is a calculated illusion, breaking up the body's outline into fragments that merge seamlessly with leaf shadows. Its paws, broad and padded, allow it to walk silently even across dry leaves, making it one of the stealthiest hunters on Earth. Where other cats stalk in visible arcs, the jaguar becomes nearly invisible, an absence of sound and motion until the final explosive pounce. But stealth is not its only gift. Unlike many cats, jaguars are capable swimmers, and water is not a barrier but an ally. They slip into rivers not just to cool themselves but to hunt. Caimans, turtles and fish fall prey to this unexpected predator. Observers have described jaguars diving completely underwater, vanishing like crocodilians, only to reappear with thrashing prey in their jaws. This aquatic adaptability sets them apart from lions or leopards, allowing them to dominate a far wider range of ecological niches. To prey species, this unpredictability magnifies fear. Nowhere is truly safe. The jaguar's hunting strategy reflects efficiency rather than frequency. Unlike pack predators that may hunt daily to sustain numbers, jaguars often succeed once every 4 or 5 days, sustaining themselves on a single large kill for weeks. Their energy expenditure is carefully balanced with intake, mirroring the precision of a capacitor releasing current only when necessary. This efficiency ensures survival in dense, competitive ecosystems where even apex predators cannot afford waste. Yet when they strike, the results are dramatic. A single jaguar can take down animals twice its weight, from tapirs to full-grown caimans. In doing so, it redistributes biomass, regulating populations and ensuring that no single species overwhelms the system. The ecological consequences of jaguars extend far beyond the immediate kill. By suppressing herbivore numbers and movements, they indirectly protect vegetation. Without predators, herbivores like deer and capybara might overgraze, stripping understories bare. With jaguars patrolling, plants gain reprieve and forests regenerate more effectively. Scientists have linked predator absence in some regions to degraded landscapes, a process known as trophic cascade. In this sense, jaguars are not just consumers but stabilizers, releasing surges of fear that maintain equilibrium. The rainforest's balance depends, paradoxically, on the violence of a few. From a sensory perspective, the jaguar navigates the world in ways humans can only imagine. Its night vision is 6 times more powerful than ours, allowing it to hunt in the darkness of moonless nights when prey feels most secure. Its sense of hearing can detect frequencies inaudible to the human ear, picking up the faint scuttle of rodents or the wing beats of low-flying birds. Its sense of smell, though not as acute as a bloodhound's, is finely tuned to chemical signals left by other animals. Each of these senses contributes to an invisible network of information, allowing the jaguar to tap into the jungle's hidden channels of sound, scent, and vibration. When combined with its physical power, these sensory tools transform the jaguar into more than a predator. It becomes a sensory node, plugged into the rainforest itself. But what if this role is even deeper? When a jaguar moves, the ecosystem shifts around it. The vibrations of its steps are not just metaphorical, they ripple physically through the soil, through termite tunnels and fungal networks, through the dense web of roots that bind the forest floor. Scientists now know that fungi connect plants in underground mycorrhizal networks, transferring nutrients and signals across species. Could the jaguar, in its movements and presence, be interacting with this hidden web? Every kill, every chase, every mark becomes part of a broader circuit of information, a surge of kinetic and chemical energy that feeds back into the system. The irony lies in perception. Humans often fear jaguars as killers, as threats to cattle or villagers, and indeed they can be dangerous when cornered or provoked. Yet their role in maintaining ecological health is one of preservation, not destruction. Remove jaguars and the circuit falters. Fear dissipates. Prey populations surge unchecked, vegetation suffers, and the balance collapses. In this sense, jaguars are not just switches, they are protectors of the current, ensuring the forest continues to hum with regulated life. And so, as the jaguar disappears back into the undergrowth, it leaves behind more than paw prints. It leaves a trail of altered behaviors, trembling prey, and recalibrated pathways of energy. Its presence is both absence and influence, felt even when unseen. It is a surge that cannot be predicted, only responded to. In the hidden circuit of the Amazon, the jaguar is not merely predator, it is spark, regulator, and living switch. The question remains, is this remarkable role the product of evolution's blind experimentation, or does it hint at something more deliberate? If the jungle truly operates as a circuit, then perhaps jaguars are not just accidents of nature but components in a living design, switches installed by the rainforest itself, or by something older, something unseen. The river is a mirror of shadows, reflecting only fragments of sky where the canopy opens enough to let in light. Beneath its surface, however, lies a presence that is neither shadow nor reflection, but something far more substantial. A body as thick as a tree trunk, gliding with the silence of water itself. This is the green anaconda, Eunectes murinus, a serpent whose very shape suggests continuity, a living current that seems less an animal than an extension of the river's flow. When it moves, the water moves with it, parting gently at first, then swirling into eddies that hint at the mass slipping beneath. It is easy to mistake this presence for the river itself, because in many ways the anaconda is indistinguishable from the waters that sustain it. The green anaconda is the largest snake in the world by weight, with females, often twice the size of males, reaching over 5 meters in length and sometimes exceeding 200 kilograms. Unlike the pythons of Asia and Africa, which sprawl across land and trees, the anaconda is a creature designed for water. Its body, massive and muscular, is not built for speed over ground, but for buoyancy and concealment in rivers and swamps. Its eyes and nostrils are positioned on the top of its head, allowing it to remain almost entirely submerged while still breathing and observing. This adaptation means that an anaconda can lie in wait for hours, appearing to be nothing more than a floating log until the sudden moment of ambush. Ambush is its language. Where jaguars create ripples of fear through motion and presence, anacondas create silence, a suspension of normal activity until they explode into violent precision. Prey animals, from capybaras to wading birds, drink at the water's edge, unaware that danger has already calibrated the strike. When the serpent lunges, its body contracts into coils with a force unmatched in the animal kingdom. Constriction is not, as once believed, a matter of suffocation. Instead, the anaconda's muscular loops exert pressure strong enough to collapse blood vessels, halting circulation and triggering cardiac arrest within minutes. Death comes swiftly, not through air denied, but through the shutting down of the circulatory system itself, as though the victim's body had been unplugged from within. Such a strategy allows the anaconda to subdue animals larger than itself. Reports of jaguars locked in fatal combat with these snakes are rare, but not impossible. Predator meeting predator in battles that can leave both dead. More commonly, anacondas target caimans, deer, capybaras, and even peccaries, prey whose struggle fuels the water with splashes that echo through the forest. Once subdued, the snake swallows its meal whole, its jaws unhinging and ligaments stretching to accommodate massive girths. Digestion can take weeks, sometimes months, during which the snake remains nearly motionless, its swollen form lying half submerged. This strategy, intermittent but overwhelming consumption, mirrors the rhythm of a current surging, then subsiding, conserving energy until the next surge becomes necessary. Water is not simply habitat, but amplifier. Anacondas rarely travel far on land, their immense bulk making them awkward and slow when unsupported by buoyancy. In the water, however, they become fluid. Their muscular coils undulate with perfect efficiency, conserving energy while allowing silent propulsion. Rivers and swamps act as their highways, corridors where their presence extends across kilometers without detection. This semi-aquatic specialization makes them unlike any other large predator of the Amazon. Jaguars dominate the forest floor, harpy eagles rule the canopy, but in the slow waters of oxbow lakes and flooded forests, the anaconda is undisputed. The ecological role of this predator reaches beyond its kills. By preying on caimans, capybaras, and aquatic mammals, anacondas regulate populations that might otherwise dominate the waterways. Their control maintains a balance that echoes across trophic levels. Too many capybaras could strip riverbank vegetation. Too many caimans could overhunt fish populations. The presence of anacondas ensures that no single species overwhelms the equilibrium. In this way, they function as regulators, much like capacitors in an electrical system, absorbing and releasing energy in cycles that prevent overloads. From a physiological perspective, the green anaconda is a marvel of adaptation. Its scales, olive green, patterned with black ovals, provide camouflage not only in murky water, but also in the dappled light of swamp vegetation. Its circulatory system is adapted to withstand prolonged submersion, allowing the snake to stay underwater for up to 10 minutes without surfacing for air. Thermoregulation presents another challenge. Being ectothermic, the anaconda relies on the external environment to regulate body temperature. After large meals, it is often observed basking on riverbanks to accelerate digestion. In cooler weather, its activity diminishes and it retreats deeper into water where thermal stability is greater. In this sense, even its body temperature follows the pulse of the river, rising and falling in rhythm with the environment. Anacondas also play a striking role in reproduction that underscores their connection to energy and flow. During breeding season, males form what is known as a breeding ball, a living knot of several males entwined around a single female, sometimes lasting for weeks. This extraordinary spectacle involves a contest of endurance, with males pressing their bodies against the females to stimulate ovulation and secure fertilization. The sight of a dozen serpents coiling and uncoiling in slow aquatic spirals is both chaotic and strangely ordered, resembling a living vortex of energy, a circuit of bodies generating heat and motion in the cool waters. For the female, often much larger than her suitors, this process ensures genetic diversity and a selection of the strongest mates. For the system as a whole, it is a reaffirmation of continuity, the passing of current from one generation to the next. One of the most overlooked aspects of the anaconda's life is its invisibility. Despite being one of the largest snakes in the world, it is rarely seen. This is not merely a function of camouflage, but of behavior. Anacondas spend much of their time motionless, lying submerged or tucked beneath roots and aquatic vegetation. Unlike predators that patrol widely, anacondas conserve energy by waiting, turning patience into a strategy as effective as speed or strength. Their survival depends not on constant presence, but on the ability to appear suddenly, decisively and with overwhelming force. For those who live in the Amazon, this invisibility translates into myth. Local legends often describe anacondas as river spirits, guardians of water, or even manifestations of the rivers themselves. But there is also science embedded in the myth. Just as electric eels of the Amazon generate actual voltage, the anaconda might be seen as a conductor, not of electricity, but of energy flow in ecological terms. Its movements along waterways link ecosystems together, connecting flooded forests to oxbow lakes, rivers to swamps. Each kill releases nutrients back into the system, whether through the snake's waste or through the scavengers that feed on what it leaves behind. Its massive body stores energy over long spans, redistributing it across time rather than space, smoothing the surges and lulls of the food web. It is in every sense a cable in the circuit, hidden, massive, silent, but essential for the current to continue flowing. If rivers are the veins of the Amazon, carrying sediment, nutrients and life through thousands of kilometers, then the anaconda is the hidden wire threaded within. It carries a different kind of current, one of regulation, fear, and continuity. Prey that survive encounters with anacondas alter their behaviors just as with jaguars, avoiding certain watering holes, adjusting migration patterns, and teaching vigilance to the next generation. The snake's unseen presence alters movement patterns in fish, mammals, and birds, creating ripples of change that extend well beyond its actual strikes. In this way, its influence spreads invisibly, much like the current in a buried cable that powers a city without ever being seen. As the camera pulls back from the still water, the surface betrays nothing. A few ripples fan outward, quickly swallowed by reflections of sky and leaves. Somewhere below, the anaconda rests, its coils pressed against mud, its body indistinguishable from the current that carries it. It is not predator alone, but participant in a deeper system, a living conductor in the rainforest's hidden circuitry. The question, then, is whether this role is the product of blind adaptation or something more deliberate. Did evolution simply mold a snake to fit the water's demands, or is the anaconda part of a greater design, one that channels life's current through flesh as much as through river? If so, then each coil of muscle, each silent glide, each ambush in black water may not be random at all, but a pulse within the Amazon's living grid. The camera narrows its gaze, moving from the sweeping canopy of the Amazon to the ground beneath. At first glance, the forest floor appears quiet, a scattering of leaves, damp soil, and the steady hum of unseen life. But then the lens drops closer, revealing something monumental rising from the earth, a tower of packed soil, sun-baked and weathered, its ridges carved by wind and rain. To the untrained eye, it looks like a lump of dirt, no different from the surrounding ground. But as the shot pushes in, cracks and openings reveal movement. Tiny, pale bodies swarm in precise patterns, vanishing into passageways as if sucked into the circuitry of a vast machine. What looks like inert earth is, in fact, one of the most complex living structures ever built. A termite mound, a superstructure of soil and saliva, engineered by insects no larger than grains of rice. Termite mounds in the Amazon are not simply nests, they are ecosystems in their own right. Some rise more than 30 feet into the air, taller than a two-story house, while others stretch far underground into labyrinths of tunnels and chambers. Many survive for centuries, outlasting the trees that grow beside them, passed down from one termite generation to the next in an unbroken chain of maintenance and expansion. Each mound is home to millions of individuals, all descendants of a single queen whose swollen body, deep in a central chamber, does nothing but lay eggs, sometimes thousands per day. Around her, castes of workers, soldiers, and reproductive drones carry out their assigned roles with a precision that suggests programming rather than instinct. The architecture itself is astonishing. Within the hardened walls, temperatures remain remarkably stable, despite the extremes of the Amazon's climate. Outside, the midday sun may push the soil above 35 degrees Celsius, while nighttime rains cool the air by half. Yet inside the mound, conditions hover near constant, protecting the fragile eggs and delicate fungal gardens on which the colony depends. This regulation is not mechanical, but biological. The termites themselves, moving in coordinated swarms, open and close ventilation shafts, repair breaches, and shift materials in ways that maintain equilibrium. They are, in essence, living thermostats, adjusting their city as needed to keep it alive. Moisture and gas exchange are managed with equal sophistication. Carbon dioxide, produced in vast amounts by millions of respiring insects, is channeled through vertical shafts and vented into the air. Oxygen is drawn in, flowing through channels in a circulation system that rivals the ventilation of ASCII scraper. In some species, water is wicked into the mound walls, where it evaporates and cools the interior through passive convection. Engineers studying termite architecture have marveled at the efficiency of these systems. Modern buildings have borrowed directly from termite-inspired designs to regulate temperature and airflow without mechanical air conditioning. What was once dismissed as instinct-driven construction is now recognized as one of nature's great engineering feats. But perhaps the most remarkable feature lies underground. A macro shot dives beneath the mound through tunnels that spread like neural pathways, branching and reconnecting, each chamber glowing with activity. Workers tend to fungal gardens cultivated on chewed vegetation, an agricultural practice that termites perfected tens of millions of years before humans planted their first crops. Soldiers patrol narrow corridors, their jaws oversized, ready to sacrifice themselves against ants and other invaders. The resemblance to circuitry is uncanny, branching lines like wires, nodes like capacitors, chambers like processors. Each pathway is not random but carefully placed, ensuring airflow, access to resources, and rapid response to threats. From above, thermal imaging of a mound reveals patterns that are startlingly similar to microchips, dense networks of pathways glowing with energy. To call these colonies superorganisms is no exaggeration. Each termite on its own is nearly helpless, driven by simple instincts and limited awareness. But together they form something greater, a collective intelligence capable of solving complex problems, adapting to environmental changes, and constructing architecture that rivals human innovation. No single termite knows the blueprint of the mound, yet the mound exists. No leader dictates tasks, yet millions work in synchrony. Communication flows through pheromones, vibrations, and touch, signals relayed like electrical impulses across a network. The colony itself behaves like a brain, each insect a neuron in a vast, distributed system. The ecological role of termites extends far beyond their mounds. As decomposers, they break down plant material, recycling cellulose that most animals cannot digest. In doing so, they return nutrients to the soil, fueling plant growth and sustaining the rainforest's cycle of life. Without termites, dead wood would accumulate, choking ecosystems with debris. With them, the forest hums with renewal. But their work does not end with decomposition. By constantly churning soil, they alter landscapes, improving aeration and water absorption. In regions dense with colonies, termite activity transforms the very shape and chemistry of the earth, creating fertile patches where vegetation flourishes more abundantly. These islands of productivity ripple outward, influencing not only plants but the herbivores that feed on them, and ultimately the predators that hunt those herbivores. Predators of termites themselves form another crucial link. Anteaters, armadillos, and certain bird species specialize in exploiting these abundant insects. An anteater may consume tens of thousands of termites in a single day, inserting its long tongue deep into tunnels to harvest workers. Yet even this predation rarely destroys a colony outright. The mound is resilient, repaired within hours, and life inside continues. In this way, termites act as both prey and engineers, fueling higher trophic levels while maintaining the infrastructure of the ecosystem. Their abundance makes them both vulnerable and indispensable, a paradox at the heart of their survival. The irony is that, despite their ubiquity, termites remain largely unseen by most who pass through the forest. Tourists and explorers may notice the towering mounds, but few grasp the scale of life within. Fewer still understand that these structures are not random heaps of dirt, but engineered cities alive with purpose. To grasp this is to realize that much of the rainforest's power is hidden underground, in systems invisible to thy yet essential to the whole. From the perspective of the living circuit theory, termites are the engineers of the Amazon's underground circuitry. Where jaguars deliver shockwaves of fear and anacondas channel the current of rivers, termites construct the boards on which energy flows can be organized. Their mounds are capacitors, regulating heat and moisture. Their tunnels are wires, transmitting signals through pheromones and vibrations. Their collective behavior is logic, processing inputs and producing coordinated outputs. The forest above ground, with its predators and prey, is spectacular, but the foundation of its energy grid may well lie in these subterranean systems. Did evolution simply stumble upon this resemblance? Or is there a deeper signal, an echo of some universal principle that shapes both human technology and insect architecture? The fact that termites and microchips share structural similarities does not prove intent, but it does provoke thought. Both are systems designed to manage flow, whether of air and moisture or electrons and data. Both rely on distributed networks of simple components, whether termites or transistors, to achieve outcomes far more complex than any individual part could produce. And both endure not because of centralized control, but because of the resilience of the network itself. As the camera pans back from the glowing chambers of the mound to the towering structure above ground, the forest seems to breathe differently. This is not just dirt, it is infrastructure, it is circuitry. And it has been pulsing quietly beneath our feet for tens of millions of years, long before the first human circuit board sparked to life. So we ask, is this resemblance a coincidence, the product of convergent solutions to the universal challenges of managing flow? Or is it something more, a message written in soil and saliva, encoded in the behavior of insects we overlook? The termites do not answer. They simply continue, carrying grains of earth one by one, maintaining their living circuit. Night falls differently in the Amazon. It is not simply a fading of light, but a transformation of the forest itself. As the sun sinks, the canopy closes like a lid, plunging the understory into a darkness so complete it feels almost physical, like a pressure against the eyes. The air thickens with humidity, the temperature dips only slightly, and the chorus of nocturnal voices begins, frogs croaking from pools, insects buzzing in relentless waves, bats slicing through unseen air currents. Yet amid this sensory overload, another kind of signal emerges, one that cuts clean through the dark, the flash of fireflies. At first the light is scattered, faint glimmers pulsing in isolation across the water's edge. Then, gradually, it builds. The pulses quicken, align, and spread across trees and riverbanks until the night itself appears to breathe with light. Hundreds, sometimes thousands of fireflies synchronize their flashing in perfect unison, turning entire groves into living constellations. For a few brief minutes, the Amazon rainforest seems to communicate in Morse code, each luminous pulse a message carried not by voice or scent, but by chemistry and physics. The source of this spectacle lies in the firefly's abdomen, where a specialized organ called the lantern produces light through bioluminescence. The process is precise. Molecules of luciferin react with oxygen in the presence of the enzyme luciferase, producing photons with nearly 100% efficiency. Unlike a light bulb, which wastes most of its energy as heat, the firefly's glow is cold light, pure and efficient, evolved over millions of years for maximum visibility. Each flash is not random but carefully controlled, the result of neural signals and chemical regulation within the insect's body. In a world where conserving energy is the rule, fireflies have perfected a system of illumination that wastes nothing. For many species, these flashes serve as courtship signals. Males of a given species produce characteristic patterns, long pulses, short bursts, or rhythmic sequences that females recognize and respond to. In this sense, the forest at night becomes a ballroom of coded messages, with each species broadcasting its presence in unique wavelengths of time. Females, often perched motionless on leaves, reply with their own flashes, guiding males to their location. Courtship is a dialogue written in light, played out across the black canvas of night. The synchrony that sometimes follows, hundreds of individuals flashing in unison, is thought to amplify the spectacle, increasing the chances of successful encounters while confusing predators. The evolutionary mystery lies in how such synchronization is achieved. Individual fireflies do not have leaders, nor do they communicate in ways we can directly perceive. Yet studies show that when one insect flashes, its neighbors adjust their timing slightly to match, like oscillators locking into phase. Within minutes, the entire population pulses together, creating vast waves of coordinated light. The phenomenon mirrors natural synchronization found elsewhere. Neurons firing in rhythm, crickets chirping in chorus, or even human crowds clapping in time. In each case, individual units adjust to neighbors, producing large-scale patterns that no single participant controls. In fireflies, the result is one of the most breathtaking natural displays on Earth, an entire forest blinking as one. But light serves purposes beyond courtship. Bioluminescence may also act as a deterrent to predators. Many firefly larvae contain toxic compounds called lucibuffergens, distasteful to birds, amphibians, and even some mammals. The glow then becomes a warning signal, an honest advertisement of unpalatability, much like the bright colors of poison dart frogs. Predators learn quickly to associate glowing prey with unpleasant outcomes, sparing adult fireflies from unnecessary attacks. Thus, what begins as chemical defense transforms into visual spectacle, with survival encoded in each burst of light. The ecological implications of this phenomenon ripple outward. Fireflies are prey for spiders, frogs, and other nocturnal hunters, yet their abundance and toxicity shape predator behavior. Their larvae, which live in moist soil and leaf litter, are voracious predators themselves, feeding on snails and worms with specialized mandibles. In this way, fireflies influence nutrient cycling, controlling populations of soil invertebrates while contributing to the food web as adults. The light show visible to human eyes is merely the surface expression of a deeper ecological role. Regulators of prey populations, prey themselves, and contributors to the rainforest's biodiversity. From the perspective of the jungle's hidden circuitry, fireflies are more than decoration. They are transmitters, nodes in a living fiber optic network. Their flashes carry information across distance, cutting through noise that sound or scent cannot penetrate. In the dense, humid air of the rainforest, where pheromones disperse slowly and sound is swallowed by vegetation, light offers immediacy. A flash is seen instantly, with no delay, no distortion. For an organism that depends on precision in courtship, this reliability is invaluable. Yet the synchrony of entire populations hints at something larger, a distributed communication system operating at scale, as if the forest itself is broadcasting through its smallest inhabitants. The theory provokes unsettling questions. Are these patterns merely byproducts of evolutionary pressures, or do they represent something more deliberate? When thousands of fireflies synchronize across kilometers of riverbank, the result is a signal visible from far above the canopy, even from the air. To an observer outside the forest, the pulses might resemble coded transmissions, ordered sequences of light produced by countless individuals acting in unison. It raises the provocative idea that the jungle, through fireflies, may be transmitting messages, whether to itself, to other organisms, or perhaps outward into the wider world. Scientific caution tempers such speculation. The prevailing explanation remains biological. Synchronization increases mating success, deters predators, and reinforces species identity. But the beauty of natural science is that it leaves room for wonder, and the fireflies' displays inspire both. Whether one interprets them as evolutionary adaptation or as communication on a grander scale, the effect is undeniable. The forest becomes not just alive, but illuminated, its energy mapped in pulses of light that mirror, in miniature, the signals humans send across fiber optic cables. The rarity of large-scale synchrony makes the phenomenon even more striking. In many parts of the Amazon, firefly species flash individually, producing scattered points of light. Only under specific conditions, often near rivers where humidity and microclimate align, do the waves of synchrony emerge. When they do, entire stretches of forest are transformed into breathing entities of light, the dark canopy above and the black water below framing a universe of rhythm. For those who witness it, the experience borders on the transcendent. For the forest, it is another layer of communication woven into its complex web. Predator-prey interactions add further depth to this spectacle. Some firefly species, particularly females of the genus Photuris, engage in femme fatale mimicry, copying the flash patterns of other species to lure unsuspecting males. When the deceived suitor approaches, he is not met with courtship, but with predation. This behavior, both brutal and ingenious, reveals another dimension of the light code: deception. Even within the synchrony, signals can be hijacked, corrupted, and used for survival in unexpected ways. In this sense, firefly communication is not unlike human networks, where information flows but can be intercepted, distorted, or exploited. As the night deepens, the synchronized pulses begin to fade, breaking back into scattered flashes. The waves dissolve into randomness, the code fragmenting into individual voices once more. For the human observer, the performance has ended. For the fireflies, the purpose has been served. Mating pairs formed, predators warned, prey deceived. The cycle will repeat again tomorrow night, and the night after, as it has for millions of years, each generation inheriting the chemical and behavioral mechanisms that keep the signal alive. From the perspective of the hidden circuit, fireflies are the rainforest's visible pulses, the clearest proof that information flows through this ecosystem, not just chemically or acoustically, but visually. They are the fiber optics of the jungle, transmitting bursts of data across distance, organizing themselves into coherent waves of light. Whether those waves are simply love songs in the dark or part of a larger symphony remains unknown. As the camera rises above the treetops, the river glows faintly along its banks, dotted with pinpricks of light. From this vantage, the forest itself seems alive with circuitry, as if lines of code were running through its veins. Perhaps evolution alone is enough to explain the spectacle, or perhaps hidden in the flashes is a deeper message, one we have yet to decode. The rainforest breathes in extremes. Jaguars strike like lightning, anacondas surge like rivers, termites build with feverish persistence, fireflies ignite the night with bursts of light. Yet suspended in the canopy, another rhythm exists, one that moves so slowly it seems to fall outside of time itself. Hanging from a branch, a sloth dangles motionless, its limbs wrapped loosely around bark, fur mottled with patches of green. To an untrained eye, it could be mistaken for a clump of moss or a termite nest, yet closer inspection reveals the faintest movement, a slow turn of the head, a careful stretch of claws, and, eventually, a measured blink. Here, in the most competitive ecosystem on Earth, where life is a constant rush of survival, the sloth embodies stillness. Sloths are among the slowest mammals on the planet, a trait that seems paradoxical in an environment defined by predators and speed. Their deliberate pace is not a flaw, but a finely tuned adaptation, one born of necessity and perfected over millions of years. Energy is the currency of life, and in the dense, resource-rich but fiercely competitive Amazon, conserving it can mean the difference between survival and extinction. Unlike predators who must expend bursts of energy to hunt, or herbivores who spend long hours foraging to fuel constant vigilance, sloths have chosen another path: extreme efficiency. Their body temperature runs lower than most mammals, averaging around 30 to 34 degrees Celsius, and their metabolic rate is nearly half of what would be expected for an animal of their size. This sluggish metabolism slows everything: digestion, growth, reproduction, and movement, transforming them into creatures that live at a pace almost alien compared to their neighbors. A closer look reveals the extent of this adaptation. Digestion in sloths can take more than a month, as their multi-chambered stomachs slowly process the tough cellulose of leaves. These leaves provide little energy compared to fruits or insects, so the sloth compensates not by eating more, but by doing less. Their heart rate can slow to as few as 20 beats per minute, dropping further when submerged in water. Their muscles are lean, contributing to their inability to generate sustained bursts of speed, but in turn reducing energy demand. In effect, the sloth has become an ecological paradox. It survives not by outcompeting others, but by sidestepping competition altogether, existing in the forest like a low-energy stabilizer in a system prone to violent surges. The sloth's fur itself reveals a hidden ecosystem. A close camera lens captures the coarse strands of hair, each grooved with microscopic ridges that trap moisture. Within these grooves, algae grow, giving the animal its greenish tint. Far from being a parasite, this algae provides camouflage, allowing the sloth to blend seamlessly with the foliage. But the relationship runs deeper. The algae may provide trace nutrients absorbed through the sloth's skin, and its presence supports entire communities of invertebrates, moths, beetles, and mites that live exclusively in sloth fur. When a sloth descends once a week to defecate on the forest floor, a risky act that exposes it to predators, the moths lay their eggs in the dung, completing their life cycle. When the larvae hatch and mature, they return to the sloth, carrying nutrients that fertilize the algae. This bizarre but elegant cycle transforms the sloth into a moving garden, a living platform where plants, fungi, and animals intertwine in symbiosis. From the perspective of predators, the sloth's strategy is both baffling and effective. Most prey animals survive through vigilance and speed, fleeing at the first sign of danger. The sloth, by contrast, often avoids detection altogether. Its stillness and algae-tinted camouflage make it nearly invisible to jaguars prowling the canopy or harpy eagles scanning from above. When threatened, a sloth may remain completely immobile, its body indistinguishable from the branches it clings to. Even when attacked, it does not panic. Instead, it defends itself with powerful claws, capable of inflicting deep wounds. Ironically, its very slowness makes it unpredictable in combat, as predators accustomed to fast reflexes may be confounded by its unhurried swipes. It is as though the sloth exists outside the circuitry of fear that governs the rainforest, immune to the cascades of panic that ripple through prey populations when jaguars appear. This immunity extends to another realm, energy regulation. If the jaguar is a spark, igniting waves of movement, and the anaconda a conductor channeling current, then Thesloth is a ground wire. Its biology dampens extremes, stabilizing rather than amplifying. By consuming low-energy leaves and moving rarely, sloths prevent overexploitation of high-calorie resources like fruits, allowing other animals to thrive. Their symbiotic fur ecosystem recycles nutrients between canopy and forest floor, feeding cycles that would otherwise dissipate. Even their slow, deliberate defecation ritual, though risky, fertilizes the soil, providing a steady, regulated input into the nutrient web. In these ways, sloths act as stabilizers of flow, ensuring that the forest surges of energy do not burn out, but instead recycle smoothly through time. Scientific curiosity has also uncovered unexpected physiological quirks. Sloths possess unusually flexible necks, with extra cervical vertebrae that allow them to rotate their heads nearly 270 degrees. This adaptation provides wide visual coverage without the need to move their bodies, conserving energy while keeping watch for threats. Their grip is another marvel. Tendons in their hands and feet lock into place when curled, enabling them to hang upside down for hours. Even in death, sloths may remain suspended from branches, claws clamped in place long after muscles have relaxed. Such adaptations underscore a body designed not for speed, but for permanence, built to anchor itself in the canopy as reliably as roots anchor a tree. But the sloth's role extends beyond biology into symbolism. For human observers, its pace has long seemed comical or absurd, earning it names that imply laziness. Yet, in ecological terms, the sloth is anything but lazy. Its strategy is radical efficiency, a blueprint for survival in a system where energy is both abundant and fiercely contested. It has not merely survived but thrived for millions of years, its lineage tracing back to giant ground sloths that once roamed the Americas. Its continued existence in the Amazon is proof that sometimes stability, not aggression, is the most successful evolutionary path. Placed within the metaphor of the rainforest as a living circuit, the sloth becomes the grounding element. Where predators create voltage spikes and insects construct circuitry, the sloth absorbs excess charge, stabilizing the system. Its very slowness becomes a form of regulation, damping the extremes of energy flow and ensuring that the system endures. Without such stabilizers, surges can overwhelm, leading to burnout or collapse. In this sense, the sloth may embody one of the forest's most overlooked functions, the quiet force that prevents imbalance. As the camera lingers on a sloth bathed in moonlight, its fur glowing faintly green with algae, the forest hums around it with frenetic life, chirping insects, calling frogs, prowling predators. Yet the sloth remains unmoved, its heartbeat slow, its breathing steady, a meditative counterpoint to the chaos. It is a reminder that in ecosystems, as in circuits, not all power lies in speed or strength. Some lies in stillness, in the ability to absorb and regulate, to persist when others burn too brightly. So the question lingers, could the sloth's deliberate pace be more than mere adaptation? Could it represent a deeper principle of regulation, a dampening field woven into the Amazon's circuitry to ensure survival? If so, then perhaps the rainforest has not only predators and conduits, but stabilizers, quiet guardians whose role is not to fight or to flee, but to balance the pulse of life itself. The camera pulls high above the Amazon basin, the largest rainforest on Earth. From this height, the landscape looks infinite, an unbroken ocean of green stretching to the horizon. Yet, as night falls, the illusion of uniformity dissolves. Lightning cracks across the sky, illuminating the canopy in stark flashes. Beneath the thunder, the forest stirs in ways both subtle and violent. A jaguar prowls along a shadowed riverbank. An anaconda glides unseen through dark water. Termite mounds exhale heat into the cooling air. Fireflies ignite in synchronized waves, their coded light rippling across the understory. And high in the canopy, a sloth hangs in absolute stillness, its moss-covered body unmoved by the chaos below. Together, these lives do not exist in isolation. They interlock, forming not just an ecosystem, but something that behaves like a circuit, an energy field wired into the very structure of the forest. The jaguar begins the chain. Its mere presence sends shockwaves of fear across the forest floor. Capybaras huddle tighter, deer adjust grazing routes, and even nocturnal rodents shift their activity windows to avoid detection. This predator's influence extends far beyond the animals it kills, shaping behaviors and energy flows in prey populations across kilometers. Ecologists call this the landscape of fear, but in electrical terms it functions more like a surge of voltage. The jaguar is a spark, unpredictable but decisive, its sudden movements cascading through the system and resetting patterns of motion and survival. Without such sparks, prey would overgraze, the forest floor would strip bare, and the delicate balance of regeneration would falter. If the jaguar is the spark, the anaconda is the current. Its massive body, buoyed by rivers and swamps, becomes indistinguishable from the water itself. With eyes and nostrils positioned atop its head, it can remain nearly invisible for hours, waiting to strike. When it does, the result is overwhelming. A capybara pulled beneath the surface, a caiman subdued in silent coils, a deer swallowed whole. These moments of violence are rare but powerful, and between them the snake glides in silence, conserving energy. Like electricity running through a wire, the anaconda channels energy through waterways, connecting different parts of the forest with its movements and its kills. Its presence ensures balance in aquatic and riverbank ecosystems, preventing population explosions that could disrupt entire food webs. If rivers are the veins of the Amazon, then the anaconda is the hidden conductor threaded within them, carrying currents unseen but always present. Beneath the soil, another system hums with life. Termite colonies, some centuries old, construct towers that rival human architecture in scale and complexity. Their mounds regulate temperature, moisture and gas exchange with a precision that has inspired engineers to mimic their designs in sustainable buildings. Within, millions of termites work like living neurons, connected by pheromones and vibrations, producing complex outcomes without centralized control. Their underground networks resemble circuit boards, tunnels as wires, chambers as nodes, ventilation shafts as cooling systems. Each colony becomes a processor embedded in the forest floor, decomposing dead wood, recycling nutrients, and aerating soil. From above, thermal imaging of termite mounds reveals patterns eerily similar to microchips, as though the Amazon had always carried its own infrastructure of information beneath our feet. The termites, unseen but indispensable, act as regulators, resistors and capacitors managing the flow of life's energy through the soil. While termites manage invisible networks underground, fireflies light up the visible world above. On humid nights, their flashes scatter at first, then coalesce into synchrony, creating waves of light that ripple across riverbanks and canopy edges. Each burst of bioluminescence is a chemical miracle, luciferin and luciferase producing photons with perfect efficiency, cold light in a world of heat and decay. Ostensibly, these flashes are courtship signals, mating codes recognized by specific species. Yet when hundreds synchronize, the result transcends courtship and becomes spectacle, a visible transmission across the dark. Fireflies are the fiber optics of the rainforest, broadcasting information instantaneously in a medium that no predator or environmental barrier can block. Whether the signal is purely reproductive or something more, the result is the same: pulses of light behaving like data, streaming through the forest in coordinated waves. And then there is the sloth. Suspended in the canopy, it embodies the opposite of sparks, currents and pulses. Its metabolic rate is so slow that digestion may take over a month, and its heartbeat can drop to 20 beats per minute. Its fur hosts algae, moths and microscopic life, transforming its body into a micro-ecosystem that links canopy to soil in cycles of nutrients. To predators, it is nearly invisible, a patch of moss indistinguishable from the branch it clings to. Its very pace exempts it from the cascade of fear that governs most rainforest animals. In this sense, the sloth is the ground wire of the system, stabilizing and absorbing excess. By consuming low-energy leaves, it avoids competition for richer resources. By moving rarely, it minimizes disturbance. Its role is not to surge, but to regulate, to prevent the system from overheating in its own intensity. The sloth is calm in a forest defined by chaos, a dampening force within the Amazon's circuitry. Seen together, these 5 species form a pattern that is difficult to ignore. Jaguars act as sparks, triggering cascades of motion and energy. Anacondas conduct current through rivers, channeling life between ecosystems. Termites engineer the very architecture that regulates flow, constructing biological circuitry in soil. Fireflies transmit coded signals in light, visible pulses of information across distance. and sloths stabilize the system, grounding the excess, preventing overload. Each role alone is fascinating. Together, they resemble the interlocking components of a circuit, a living grid humming across millions of square kilometers. This perspective reframes the Amazon not merely as an ecosystem, but as a functional machine, one designed to manage energy, distribute signals, regulate balance, and ensure continuity. Science offers clear evolutionary explanations for each adaptation. Jaguars evolved powerful jaws to hunt efficiently. Anacondas specialized for aquatic ambush. Termites perfected social architecture. Fireflies synchronized for courtship. And sloths slowed metabolism for survival. Yet the convergence of these adaptations into something resembling circuitry raises questions that go beyond science. Is this resemblance coincidence, the inevitable result of natural selection solving universal problems? Or does it hint at something deeper, a design embedded in the forest, one that uses life itself as components in a greater system? Even if the answer lies only in evolution, the result remains extraordinary. The Amazon functions not just through biodiversity, but through the flow of energy, kinetic, chemical, electrical, and informational, managed across scales from predator-prey interactions to microbial symbioses. It is a circuit built of flesh, soil, light, and water, and like any circuit, it hums only when all its components are intact. Remove the jaguar and the spark disappears, prey populations surge and the flow destabilizes. Remove the anaconda and river systems lose their regulator. Eliminate termites and the soil's architecture collapses. Without fireflies, the night loses its signals. Without sloths, the grounding balance is gone. Each loss is not just subtraction but disruption, a broken link in the chain. The final image returns to the aerial view. The storm continues, lightning arcing across the basin. From above, the rainforest appears alive with motion and pattern, predators shifting silently, rivers gliding with unseen coils, mounds exhaling warmth, lights flickering in waves, sloths swaying gently in trees. It is not chaos, it is system. The Amazon isn't just alive, it is wired. And so the final question lingers. If this truly is a living circuit, who or what designed it? Is it evolution's masterpiece, the ultimate expression of life adapting to balance itself? Or is it something older, a program written in biology long before humans arrived, one that still runs in the background of Earth's greatest forest? The answer remains hidden beneath the canopy, pulsing quietly, waiting to be decoded.